Good morning, everyone.
Good morning.
I am glad to see your bright, smiling faces here today. If it was up to me, I'd be taking a much-needed siesta from the everyday work. So I appreciate you all being here, and especially to talk about something that I've really enjoy, machine learning. My name is Jackson Pontsler. I am a graduate student here at the University of Utah. And one of the emphasis in my degree is machine learning. I will be attempting to do something that when I told my professor I was doing this, he thought I was a little crazy. I will attempt to take an entire graduate student course and condense it down into what are the most common algorithms in machine learning, their pros and their cons, and their basic applications. This is a very fast pace, and I don't want to lose people. If you have questions, please feel free to stop me and ask, because I'm sure that there will be a couple of you that will have the same question. That being said, my algorithms that I have, the basic algorithm slide, will only be a general outline. If you were to just plug it into any program, it will not run, but it's a general outline for you to write in your own programming language of choice in order to implement these programs. And with that, let's get started. The algorithms, what we will be covering today is we'll first talk about what is data. We'll be talking if learning is possible. Some data sets are learnable, others are not perfectly learnable. And we will discuss what those problematic areas may be. We will then get into the basic algorithms of machine learning. Decision trees, nearest neighbor mapping, boosting, perceptron, and support vector machines. If there is time, we will also discuss the winnow algorithm. First question I have is right there on the board. What is a cat? If someone was to come up and ask you to describe to them a cat, what would be some of the features that you would answer?
About 8 to 10 inches tall, rough fur, various colors, eyes with ears.
Exactly. Now, those are very good. What the cat is the cat is a label. We specify that this thing with these features is a cat. And sometimes we have a multi-label space. So instead of deciding if something is a cat or not a cat, you may be asked to classify if a certain animal is a cat, a dog, or a rat. If you were to then put these into a binary situation, it would be, is this a cat or not a cat, a dog or not a dog, or a rat and not a rat? Now, what you mentioned earlier is what's known as the feature space. As we mentioned, perhaps it is retractable claws, size, furry tail, panting with the tongue or name, because I've never heard a dog named Squeaker before. This is a general outline of what our data will be. There will be a label, and then there will be features after it. And typically these are represented by a number. The second question we have is learning even possible? Could a straight linear line classify a parabolic line? It'd be very difficult. There are tricks in machine learning, such as a feature transformation, that we can use to help classify or change from one line to another. However, there is a trade-off with this. If you were to get an exact perfect line that would classify your data, and this line may be absolutely crazy, just think about like if you took the entire cursive alphabet and put it together in a single line. This is a typical example of what's known as overfitting your data. And here is the giant struggle of machine learning. How can we create a classifier or algorithm that is expressive enough to correctly classify our data, but yet does not overfit the data? And the reason why we want to avoid overfitting data is because of a common feature called noise. There will always be noise. If you have sensors in your robot, there will be noise in the sensor. There will be problems or faults with your data. And if you overfit your data, you may lose the true function. We will be discussing also in our classes, our algorithms, some of the changes that we can do to try and go for more generalization or more fitting of our data. The first thing I want to talk about is known as decision trees. By raise of hands, how many of you have heard of decision tree before? Wow. More than half. That's really good. What a decision tree is it's, well, like I was saying, it's, as the name implies, it's more or less a tree where we take a look at our data and we look at individual features. For example, if the label I was looking for is whether I should play tennis today, the features would be the outlook of the weather, the humidity, and the wind. These are features. The numbers that they correspond to for outlook could be, is it sunny, is there overcast, or is there rain? And for the humidity, high, normal, and for wind, strong and weak. Your algorithm will look at your entire data set and will build one line at a time, looking at the feature space. For example, if I had a point that said, yes, because the outlook is sunny and the humidity is high, the humidity is normal, I will play tennis. And it would build that small branch of the tree. It would then go down to the next line of data and say, no, I'm not playing tennis today because the outlook is sunny and the humidity is high. It will go through its entire data set and build every branch that you have in your data. And then your algorithm will go and prune the tree. It will look for overcast. And it said, no matter what other feature space, no matter what the other features were, wind, whether it was strong or weak, or humidity, if it was high or normal, no matter what, if there was overcast in the outlook, I will go and play tennis. And it will cut off the rest of the branches and put that label right there. The general algorithm involves us creating a decision tree node. It will have a label on it that defines the feature, such as the wind, the humidity, or the outlook on the weather. And then it will have a list or a series of pointers to the other branches. You will then start your tree with this key node in the main program. And then you will look at you will read in a string of data and follow it to the end of your tree. And then you will attach the children and the feature spaces to that node with the label. You will also probably need a function such as find end, where you will have your tree go down one of its branches or go all of its branches, where it can look to find out if there is a copy, if there are multiple of the same label at the end of the node. As I mentioned before, if the outlook was overcast, then it didn't matter. We always went and played tennis. The pros and cons of this function. We can represent any function with a decision tree. This is by far one of the most powerful algorithms, and it's very simple to use. But the biggest con is we will overfit the data and include the noise. That's because as we're going along, if there's a slight variation and my sensor said, oh, you know what, it wasn't, the outlook today was not overcast, it was sunny. Even though it's different than what it truly was, the data will fit the wrong and erroneous data that we had. This concludes my topic about decision trees. Any questions before we move on? Yes? What overfitting is in our data, we will inevitably have noise. A best way I can put this is we recently had a global data competition for Big Data Utah. And with that, we were given data about the weather. But these involve sensors, and sensors don't always behave as you would expect them to. Sometimes they don't have any, sometimes they have missing labels. Most of the time, they mess up with their measurements. What overfitting does is overfitting will look at those data and read it in saying this is automatically true. It makes an assumption that this is true data, that there is no error and there is no noise. That is what overfitting is.
Related to the signal noise ratio, like are there ways to determine it?
Those are done more in other algorithms, but for the decision tree, it just overfits in general. It's the most expressive. It can express any function there is, but the problem is it will overfit. Other algorithms that we'll talk about not overfitting and talk about how we can reduce that noise. Before we get on to the next algorithm, I want to talk about what's known as cross-validation. The next following algorithms that we will talk about will ask us to give them additional parameters, known as hyperparameters. For example, the next algorithm that we'll talk about is nearest neighbor mapping. The hyperparameter in question is how many nearest neighbors do you want to compare them to. If you were to do a one-to-one person, meaning I look at my nearest neighbor only, the first one, and take on his label, that is more prone to overfitting. But if I was to say, you know what, I want to look at the 5 closest neighbors next to me and take the majority label, that reduces overfitting and goes for more general ideas. When you implement cross-validation in your code, what you will eventually do is you will take your data set that they will give you and you will cut it where you have a large amount that you will train on and a small set that you will test on. You will then run your algorithm with different hyperparameters and see which hyperparameters is the algorithm to best classify this small test set that you have. By doing this, you can choose the most optimal hyperparameters for the algorithm to use from then on. Is there any questions about cross-validation? Either I'm a really good teacher or you're just very sleepy because it's early in the morning. If there's no questions, we'll move on. I mentioned about nearest neighbor mapping. This is where we take our entire data set that we had, and we store them as arrays. And then we look at our test data coming in. The test data will then go through our entire data set, looking for the closest matching data itself. It will look to see which feature space closely resembles the test data point we got. Going back to our example of tennis, if it was well, at least you made it here all right. Going back to our tennis example, we had 3 features: outlook, humidity, and wind. If we had a data point that was overcast, high humidity, and strong wind, it would look through to see if we already had a point in our data with overcast. We would look through our data set and see if we already had a point labeled overcast, high humidity, strong wind. If we did, we would assume that label, saying we already have that point. If we were to look at, instead of 1 nearest neighbor but 3, we would look to see, oh, we have one that perfectly matches. We have one that has overcast, weak wind, and high humidity, and we have one that's overcast, low humidity, and high wind. And we look and see what all 3 of those labels are, and the average of those labels would be what we classify the data as. But a better example would be a picture. This is an example of how it would look. You would have all your reds. These are hypothetical boundary lines. And if your data point fell within this red region here, its closest neighbors would be red. If it fell in the green, more than likely it'd be green. And if it fell into the blue area, it'd probably be classified blue. But something interesting to note here is if you look at the blue and green areas, you'll find some intermingling of data. Some blue spots are in the green data, but it's still labeled a green section because green is more predominant and are more closer than the blue points.
So the color of the dots are the true.
Are the label.
The true.
Right, so going back, red could be dog, green could be cat, blue could be a mouse. As I mentioned before, your basic algorithm, you will have a list that will contain all points in your data. And then you will take a single point and go through all your points. You will calculate the distance of that point from every single other point in your data set. You will then look for so many minimums. Maybe you have only 1 minimum. Your hyperparameter was look at your 1 nearest neighbor. Maybe it was 2, maybe it was 3. You will get all of those, you'll get the number of neighbors that you chose because of cross-validation, and then find the majority label. And even if it was wrong, even if that will go into the pros and cons. You will take the majority label. Here's the pros and cons. As with decision trees, we can represent any data type. And another pro we have is we have this trade-off between overfitting and underfitting. You can choose the number of neighbors that you compare yourself to. If you choose the single nearest neighbor next to you, you will overfit your data. But if you were to compare yourself to the closest 3, 4, or 5 nearest neighbors, you will get more general functions and more general mapping that is less expressive, but is less prone to the noise. The biggest problem that you have is you need to be able to find out what is the best closest, the best number of neighbors to compare yourself to. And that's why I talked about cross-validation earlier. The other hard thing we have is you typically need to normalize your data. You're taking distances. So if we were to measure caffeine levels in coffee, you'd be talking about milligrams. But then if we were to comparing it to the overall, the amount of milliliters of liquid in their coffee, you would have a huge amount of milliliters, but very small amount of coffee, a very small amount of caffeine. And the large data set of the milliliters, the large numbers, would overpower the number of caffeine if you were to compare. This is for like a hypothetical data set where you were looking at for example, what kind of drink am I drinking? Mountain Dew, coffee, whatever it is, based on perhaps the amount of liquid in the vessel and the caffeine that's in that vessel as well. This concludes the nearest neighbor algorithm. Any questions?
So you use cross-validation as a way to determine the number of nearest neighbors?
Yes.
Okay, so that's an optimization, and that's dependent upon the data set that you're.
Exactly. That's why it's recommended in cross-validation. Labeled data is very expensive. So with that labeled data that you have that you're training on, take a small sample of it and you never train on that. You'll train on that at the end. You will run cross-validation on that small set of training data and then test them out against that other small set of test data. Find the best hyperparameters and then you train on all the data at the end.
In any given data set, can you render multiple labels?
What's that?
Can most data sets give you any number of labels that you can test against?
Yes.
So, but in general, you look for only one.
One more time.
That's not multi-classifier.
So in general, you only do.
Oh, multi-classifier? You would,
That's multi-classifier.
yeah, for a multi-classifier, are you talking about like if we were talking about a cat, a dog, or a rat for a classification?
Sure.
Then yes, K-nearest neighbor would do that.
Okay.
Other ones, like we will get into, such as the perceptron, you will only be able to do a dog and not dog. But the beauty of the K-nearest neighbors is you can do multi-label classifiers. For example, I did this in the tic-tac-toe data set, and it was, the data sets were win, lose, or draw. So that was the classifier. Would I win, or would I lose, or would I draw? The next thing we'll talk about is known as boosting or ensembles. Boosting is an interesting idea. The argument comes, if I have a very weak classifier, could I turn it into a strong one? This takes an example of, if I can correctly classify my data 51% of the time, could I make that into an algorithm where I can correctly classify 99, 98, 100% of the time? That's what boosting and ensembling does. You take a weak classifier and you will stack them together to get a much more expressive classifier overall. A basic idea would be the following. Let's say I have this hypothetical data set. I have my first classifier here, H1. It can correctly classify 2 positive points. They will misclassify 3 positive points every time. You say, okay, this is all right one. It's a weak classifier. Let's see if I can make another weak classifier. And what boosting does is it will take the points that you mislabeled with your first classifier and make them bigger. So you're no longer seeing those as a 1. you're reading those as a 2. It will also look at every point that you correctly classified with the previous classifier and decrease them. So instead of having a weight of 1, it will give them a weight of 0.5. It will then look at the data set again and create another weak classifier. So if you see the second one, we are able to correctly classify the 3 positive points that we missed last time. But now we miss, and we're incorrectly classified 3 negatives. So we decrease everything we labeled correctly, and we increase everything we misclassified. And then we perform the algorithm again. The hyperparameter in this algorithm is the number of times you will repeat this. The less times you repeat this, the more general function you'll get. The more times you repeat it, the better expressivity you'll get, and thereby cause potentially overfitting data.
Are the weights hyperparameters?
The weights are classified. The weights I'll show you later on, but the weights are determined by the error that the classifier gives it.
Okay.
The hyperparameter here is the number of weak classifiers.
Okay.
In the end, you get a classifier that looks like this. You add up the weight on each of the classifiers, and you have them guess using that, using their individual weights. And it'll give you that expressive function there. Let's get into the algorithm. You find the classifier whose weighted classification error is better than chance. There's the weight you calculate there. The weight you calculate is by its error. And it's not the error of the previous one, because we have been modifying our data set as we've been going along. By this time, a certain point may no longer have a value of 1. The data points may have values such as 3, 4, 0.5, 0.25. By taking this weight, this is how you classify your weight for all your different linear classifiers. Not linear, all your different weak classifiers. And that's how you, I'm losing my voice here. That's how you assign the weight there. You then determine the update for the next one. So you update the values of the weight for the training sample. That's how you choose what it is. The reason why that is not set, I've been giving the example of doubling or halving the values. It's because sometimes if you were to get a classifier that correctly classifies all the data except a single point, it should have more weight on it. It should get a bigger vote than something that can only classify 2 points and then this classifies 5 other points. And then you take the sum of all your classifiers with the determined weights, and that is the label that they will do. Now I know this is a lot more vague here than the other ones, but the reason why it's a lot more vague is because I can't tell you how you create your weak classifiers. That is up for you to decide. A lot of people just kind of take a half. They do a halving algorithm, just take your data set, cut in half, where all sides on one side are one label and all the rest have the mess ups. That's typically how this one is done. The hyperparameter is the number of classifiers that you have. How to determine your weight is given by the error equation up there. And then you update the weight for the training example based on that algorithm down there. Any questions?
So this is ADA boost, and there's different kinds of boosting.
Yes.
What's different? Is it like how you do the weights or how you update the values?
From how I understood, it's a mixture of the weights and the values.
Okay.
This ADA boost was just a more mathematically way of being able to do the most optimal update.
Yeah, okay, yeah.
Pros and cons. AdaBoost is probably one of the most fastest algorithms that we have. It's easy to do, and the hyperparameter is really simple. You can go along in your cross validation per se. Most people for hyperparameter, you don't even need to really do cross validation. You will just test yourself and wait till your overall expressive function is able to classify all your training data. So for this one, you don't even really need to run cross validation. You just keep track of the error that you have with your entire training set as you go along. And then you stop when you find that error becomes 0. The cons, this is, like decision trees, probably one of the hardest between overfitting. But this is also prone to underfitting. You could say, all right, I'm going to stop at the 0% error and cut myself off two rounds early. You may have underfitted your data and may not have gotten the best function that you could. So this is one of the fastest algorithms, but it's the hardest to find the balance between overfitting and underfitting. We will now be talking about the perceptron algorithm. Probably one of the most powerful algorithms that we have. What the perceptron algorithm does is it works on a basis of a linear classifier. That means that it will only be able to determine if it's a certain label or not a certain label. It will only be able to determine if it's a dog or not a dog. It will update its errors based on the mistakes that it makes during training. It will update its accuracy during training because this is the first algorithm that is known as an online algorithm. It will start at some point. Typically, people will start it at a weight of 0. And I'll get into what weights are later. But the weights basically express the line you are trying to form. So they'll start at the line at 0. And they'll see if the point that you give it from your training set is correctly classified. If it doesn't, it will update itself so it does correctly classify your data points. The updates, though, are dependent upon whether it makes a positive or a negative mistake. Well, a mistake on a positive or a mistake on a negative. Those are the updates there. The best way I can describe it is with pictures. So this is if we made a mistake on a positive example. That blue line is where our weights or our classifier is currently at. Where everything on the right, so that arrow that you hold, is supposedly the positive side. And we have a point on the left that is the positive side. It realizes that it has made an error. And so it will update, it will change its weight vector by taking a percentage of that point and subtracting it from our weight vector. Well, adding it to our weight vector. This gives us a new weight vector in general. And so you can see that that blue line has moved because it made a mistake on that point. The same thing happens with a negative. That blue arrow shows where everything should be positive. And we see that we've made a mistake on a negative. That point should be negative. So what do? We take our previous weight vector and we move it from that by a part of that point that we saw. The hyperparameter here, I should mention, is called the learning rate. And that is the amount that it moves every time it makes a mistake. These slides show a learning rate of 1, where it'll just take that feature and just add it to the weight. And depending on the mistake, it will either add or subtract it completely to move the line or the classifier around. By doing this, over the series of your whole data set, you will more than likely, if the data can be linearly separated, meaning that if you can draw a line that could correctly classify the data, it will converge onto that if you have enough data points. If you do not have enough data points, it will get in within so much distance of it based on the amount of data that you have. But that is based upon learning theory, and I decided it'd be best to kind of avoid that for the scope of this class. The basic idea of learning theory is you need to have enough samples in order to train your classifier or train your algorithm. You cannot train an algorithm with only a single point. You need to have many points. But that's the general idea of the perceptron. You will make, if your classifier makes a mistake on the training data, it will take the features of the previous, of the point that made a mistake, and it will update itself to include those, shifting the classifier overall to make sure that your point is correctly classified. Yes?
So, this combines with the previous example in that we use this to create those lines that would separate out our data from one side and let the other side, so we use a different algorithm to weight them and then make decisions.
Yes, you can use the perceptron with data boost. The beauty of boosting is that you can use any classifier per se. You can use decision trees. A common one could be decision stumps. Have anyone ever heard of like a random forest before or anything like that? What a random forest is a set of very small and inaccurate decision trees. But you use all of those and you boost them with their individual weights, and they can classify. Such as with the perceptron. You can boost perceptron by taking a series of them and have them create the classifier. Yep.
So in your pictures here for the perceptron, is that like a classifier with 2 features?
Yes, this is like for a classifier with 2 features.
Okay.
But this can expand to a lot more features. I did this with a feature set of 100. This can go to 1,000, 1,000,000. Very large. Another thing I should, no, that one. Here is the basic algorithm of the perceptron. You start with your line. Some people do random numbers in your weight vector. You don't need to do that. You can start with a 0 weight vector. And then you go through your data set. You will look and you basically take a guess. Your weight vector attempts to classify the point by taking the dot product with the feature space of the label that you're coming in with it. This will then have it make a guess, whether it be positive or negative. You then look at the true label of the point that you gave it, and you see if they match. If they match, you don't update. You did it correctly. But if you mess up, you update your weight vector with your learning rate and the feature space, and add on the feature space of the point that you messed up on. And you will do this for all your data. Another thing that's important is maybe you only have 100 points in your data set. Perceptron may not converge within that 100 steps, 100 points in your data. So what is typically performed for it is running what's known as epochs, or you run through your data multiple times. This will help it to converge into the most optimal point that it can get. Another thing I want to mention, that as you go between rounds or epochs, shuffle your data in between, meaning you randomize the order that you're going to see your data. This is to avoid any skewing that the ordering of the data may present to your perceptron. And this is how you kind of avoid some of the pitfalls of it. One of the good things about perceptron is it does avoid overfitting, but it still can be affected by noise. Hopefully, though, this noise will be counted as the errors that it makes. And what I mean by that is, suppose that you have data that is misclassified right in the center. So you have stuff on the left that is true, well, stuff on your right that's true, and stuff on your left that is false. And then you have some intermingling here on the middle. The perceptron should converge in the middle. And the errors that it makes are the noise that you have. So this is one of the best algorithms that we have that avoids noise in general. But it's still effective. If you have a significant amount of noise, it will hurt it. But whenever you have noise, it hurts algorithms in general. Before we move on, is there any questions?
Is this presentation in the context of a certain tool?
No. I'm giving you the basic outlines of the code. So that way, in your own language, whether it's C, whether it's Python, whether it's R, you know what the general outline would be in order to implement it in your own language. But good question. If you were to use Python, I'm very familiar with Python, and there are libraries that you can type in. They already have functions you can do in like random forest or perceptron, and they ask you to give a pointer to your data set and we'll run through it. But the data needs to be in a certain format and other things. Any other questions? Okay. Looks like we have a little bit of time I was hoping for. So that means we have time to talk about what is the winnow algorithm. The winnow algorithm is very similar to the perceptron algorithm. The winnow algorithm, though, works by, instead of taking a part of your feature space and putting it into your weight vector or your weight classifier, it will look to see where they disagree and promote or demote features in your weight vector. I will get into this later on. I will give you a better example of this coming up. But the big power that this has is, let's say you had a weight vector that worries about 10,000 to 1,000,000 features. But in that space, only 10 of them are relevant. The winnow will move faster than the perceptron to give you the optimal weight vector that best classify this point. Because the winnow will shrink the ones that are irrelevant to 0 and increment the weights that are important to a high number. Okay. Here's an example of how the winnow works. You start with your weight vector being all ones. And then we're going to take a look at our first data point. Our first data point is going to be an all one with a positive label. We make our prediction by taking the data point, crossing it with our weight vector, and seeing if it's greater than 0. There is no error. We predicted that that would be true. It is true. We don't update our weights. Let's say we did make a mistake. So we drop all the way down to the fourth line, where it's 1 and all zeros, and white, and it has a true label. We say that it's less than 1. But when we take the weight vector of it, it says, oh, nope, it's supposed to be 1. It's supposed to be a -1. We've made a mistake. So we go through and we look to see what was the feature. What features were 1 in our X point? In this case, only 1, the first point. was the only one in there. And we doubled the weight that's associated with it. So our weight vector that was all ones is now a 2, and then all ones. We keep on repeating this. We make a mistake. Oh, I should mention, this is for the idea that we have 1,024 features in our weights. But the true function is the conjunction of x1, x2, and 1,023 and 1,024. So the big ones that should be boosted by the end of this should be the first 2 and the last 2. All the ones in between should be zeros. So we take a look at our second point. We go down to line 5, where it's a 0, a 1, and all zeros. We're taking the dot product. Our classifier said it should be false. We look at the label, it says it's true. We learn we made a mistake again. We look at that example, find the ones that include a 1. We see that's the second one. So we go to the second weight of our classifier, and we double it. So now we have a 2, and all ones. And you repeat this as you go along. Now let's say we made a mistake on a negative example. If you look at the third to last line, you'll see where our weight vector is at. 512, 256, 512, 512, 512. Let's say we got to this point in our training set, and this is the first time we make an example in our negative. We look to see what are the values that are ones. In this case, the third and fourth in our weight are the only ones that are ones. So that means we go to our weight vector and we decrease the values that are associated with the third and fourth. So beforehand, they were 512. Now they're 256. By repeating this and getting errors on a positive and a negative update, you will eventually come to a classifier or weight that will look like the following. You will get a number that's 2,024. When a weight becomes that, you lock it in, it's a match. And then you'll get stuff that are not 1,024. You take those and put them to 0. This gives you the true function that we were trying to describe. The conjunction x1 and x2 and x 1,023 and 1,024. I know this is more of a vague, but that's why this one is kind of harder to explain. But that's because instead of taking a part of the point that we did, like in the perceptron, we are going to compare and see where, first off, if the mistake was on a positive or a negative, and then incrementing or decrementing those weight values that were 1 on that data set. Go ahead.
So in the X vector, is that all permutations of 1 and 0?
They don't have to be. They could be permutation, anything between 1 and 0.
How are you picking what goes in the X vector?
That's your data point. How do I put this? So your question is, how do I determine what's going in there? For this,
That's the data?
right,
That's the data. Okay.
right.
Oh, okay.
X is the data.
Okay.
Good question, Paul.
So the criteria you use to determine if it's 1 equals positive 1 or negative 1, is that just like the majority of data points in the vector or 1?
It's the dot product.
Of the dot product?
Yes. You take your weight vector and you dot product with your data coming in. And that, maybe I wasn't as clear, but that's the exact same on the perceptron. You take the dot product of the data coming in with the weight vector you have. And that is the weight vector's prediction of whether it should be positive or negative. Good questions, really. I know I'm not the best teacher. If you have questions, please. Okay. We will get on to the final algorithm I wanted to talk about today. And that is support vector machines. Support vector machines are one of the most common algorithms out there in the workforce today. Support vector machine acts just like the perceptron, but does something a little bit more important. It goes for the most general function that it can get. And the best way I can talk about this is basically comparing it to the perceptron. As we talked about, the perceptron will stop changing itself when it's able to correctly classify the data. Now I have a question for you guys. Let's say those three lines there, the red, the purple, and the green, are different weights that we could have. The reds are one label, the blues are the other label. What line is probably the best classifier that we have? The green.
I like the green.
Why do you like the green?
It maximizes the margin between the two.
You just said something very important. It maximizes the margin. So what is the margin? The margin is the distance from our classifier to the nearest point. Support vector machines are different than perceptron because support vector machines will maximize the margin between the possible labels. So here's a better picture of it. So let's call that line, or the weight vector we have, known as a hyperplane. And then we once again come to our dots. We will have our maximum margin, or the plane will be in the middle of the distance between the 2 points. That's what the support vector machine does. The support vector machine also can be simplified to work on only the points that are the closest together. So I have points clear off in Provo and I have points clear off in Logan. Those are not going to have weighted effect on my algorithm. They'll be the ones that are very close. Here is the basic code. Initialize your weights at 0, and we'll go with the epochs again for the idea that, you know, maybe we're not going to converge on what the best line should be right at the beginning. But if I run through my data enough, I'll come to what the line is. We're also going to define the learning rate here. The learning rate can either be a hyperparameter that you chose, or better yet, the learning rate can be a function of 2 hyperparameters that you have here. Those will be the weight of your first step and rho, which is a control of the generic step that you should take. And so what goes on is you will first look to see if you made a mistake. If you made a mistake, you will take the learning rate, and then you'll take your weight minus the learning rate times your first step times the label times x, your data set. And you will update your weight vector accordingly with that equation. However, even if you were to see your first point and you label that correctly, your algorithm will say, okay, that's correctly classified. I'm going to reduce myself to maximize the margin. So it will subtract a part of itself. So basically, if it was all ones, it would cut itself to halves and see if it will be able to classify correctly. Now, mind you, I mentioned before that the learning rate can be a hyperparameter. So you can have this learning rate be the hyperparameter that you chose, or you can have the learning rate be dynamic, meaning that you gave it 2 hyperparameters and it will keep track that as time goes on, the learning rate will get smaller and smaller and smaller with more and more points that you see. This algorithm is probably one of the most common out there in the workplace. Any questions?
One thing I struggle with is when I know I need classifier, which classifier,
Mhm.
based on the data. I know that's not specifically related to
The class, yeah.
class. Do you have any thoughts on that?
Thoughts? Well, this actually kind of concludes where I was at, so I can, if no one minds, I can talk about that.
I mean, one approach I think is do them all, and which one is the best classifier, but that's probably not the most.
You're right. That's actually one of the most common things you can do in machine learning. You have this list of algorithms. Say, okay, if I throw everything at this, throw it at it and see what sticks. Another kind is boosting or ensembling. You say, I have all these classifiers. Why not take all these classifiers and then have them make a vote? My best answer to you is, this is if you have no information about your data set, right? You have no idea if it's already linearly separable. From my personal experience, what I would first do is run what's known as a feature transformation on your data set. The reason why I say this is because if we were talking about it being a straight line, that line may be parabolic, maybe quadratic, maybe some kind of cross between all the features together rather than having them have a weight on it. So the first thing I do is I would transform and make it at least a quadratic set. Second off, I would try and throw out the idea that I'm going to be able to get everything correctly. I'm going to say I want to pick the one that gives me correctness up to a certain amount. So that's in your individual situation. You may say, I can live with being right 90% of the time. I know that's hard because we talk about wanting to be right 100% of the time with our trading set, but as I mentioned before, the biggest fight we have is if we don't have an inkling that our data is linearly separable, then we know we're not going to be able, then we know that we're probably going to be overfitting. So first off, I would try the perceptron or the support vector machine to see if both of them agree that this can be separated by just a line. If that's not possible, I then take the coordinate transformation where I would kind of take the cross of the feature. So I take feature 1 times feature 2, feature 1 times feature 3, feature 1 times feature 4, and I calculate a whole new feature set with that. I'd run perceptron SVM to see if that is linearly separable. If not, then I would resort to probably mapping and do the k-nearest neighbor algorithm. Does that help?
Yeah.
That would be my approach, because if you can get to a linear, it's very quick to calculate for the new points. But if you're looking for the best that you can do at that time, and a simple transformation will not help the SVM or the perceptron get you a very good classifier, then I'd swap to mapping and choose and run cross-validation to find the best number of neighbors I should compare myself to. All right, any other questions? If not, you are free to go. Thank you very much. The slides and the presentation will be on YouTube. So if you want to go through and look at the slides again, or if you want to contact me, you can follow me through there. Also, please fill out the summary sheet when you have time. Thank you.